So first things first, have open the applets page and the stat blue page for as we go into chapter 12 today. Chapter 12, which is on regression analysis. We're not going to go uber deep. If you've ever taken an AP class, we're not going to do logarithms and linear transformations. So it's less than what they did there. However, we will be adding a hypothesis test on R, the coefficient of, or the correlation coefficient. But start by getting those open, and then this is where we're going to start. We are going to start by saying if these were exam 1 and exam 2 grades for 10 students selected at random, and we know that the exam scores in general are normally distributed, that's a key item there. Is there reason to believe that students are getting better? So that's what we're going to try to figure out. Utilizing Stat Blue, graph the data. You'll actually find one of the tabs says linear regression. I don't know if it it says bivariate data. It might say 2 variables. But whatever the tab is, it's on the far right side of Stat Blue, maybe the first one down, linear regression for bivariate data. We're not doing a multivariate assessment with this. So go ahead and get that data entered. Create a graph. It'll give you an equation for a regression line. And then this is where we're going to pick up after a few minutes after you've entered this information in. So if you need to and haven't ever experienced this before, grab your book as another tab. Look to chapter 12. Search for correlation coefficient and coefficient of determination. Read a little bit so the first time we talk about it, you're like, oh, I know what we're talking about. So I'm going to go in the next slide here in a second. So again, you've entered this into the Stat Blue exam 1 as the variable on the left-hand side, explanatory. The exam 2 will be the one on the right. That's your response variable. Or if you want to think X and Y or independent, dependent, or however you think about it when you think about graphing. You graph the data you found, and then it'll find a regression line for you. So you did this. You put those numbers in. Explanatory X, that was the exam 1. Response Y, that's exam 2. And then include a regression line. Like I said, if you wanted to do the analysis for a hypothesis test, you could do that. It'll actually print out a few more graphs for you. But to get us started, that should have been, if you just did the first checkbox, that's what your graph should look like. All right, so here it is, and it puts the line on there. All right, and then here is the equation that it tells you. And I'm going to actually switch it up just a little bit and add some notation for how we're going to rewrite these. In the past, you probably wrote equations like this. Y equals mx plus b. When we move to statistics, we of course have to write it differently. We will write it as, in this case, y hat equals a plus bx. I want you to point out, or I want you to notice in this b is the slope. This a is the y-intercept. Why do they do that? I honestly don't know. But most stats textbooks are going to write it like this. Y hat equals a plus bx. This is where you, as the critical consumer and knowledgeable person of mathematics, needs to remember the m was the slope. That's the number in front of that's the coefficient of x. B is the coefficient of x here. So in this equation, b is the slope. And I'm writing y hat. The reason why is this line predicts values. It doesn't give the actual values. So because it's a predictor, much like the other ones we've had, x bar, p hat, y hat. They're all predicting what's going on. X bar predicts mu, p hat predicts p, y hat predicts y. So if this is my prediction equation, my actual equation is y equals alpha plus beta x. because again, we typically use Greek letters to represent population values. So if I had the whole population of students could plot all of their data points, the slope would be b, beta. Here, we don't know what it is, so we call it b, and our equation down here I'm going to rewrite as y hat, or exam 2 hat, equals 9.814 plus, oh no, that's my b. I'm looking down here to look at what they have written. So the 0.918, so I'm going to rewrite it the other way then. We're going to rewrite it as my intercept first, 1.741, which is positive, plus 0.9814x, where x was exam 1. So it gives me this equation. Typically, statisticians write it like this. These values, the y-intercept, the interpretation of the y-intercept would be, if I scored a 0 on the first exam, this would all be 0, I would expect y hat on the second exam to get 1.741 on my test. All right. 0.9814 is my slope. The interpretation of slope is, for every 1 point that my exam 1 score would go up, my exam 2 score would go up, positive, by 0.98. So slightly less than 1. So it's going up, but not as fast as the first ones did. And then the correlation coefficient. Correlation coefficient is R, 0.696. The correlation coefficient is my assessment of the linearity of the data. The correlation coefficient tells me, is this data linear or not? R, the most R can ever be, is positive 1. The least it can ever be is negative 1. If there is no linear relationship, R will be close to 0. If there is a strong positive linear relationship, R is equal to 1. If there is a strong negative relationship, R is close to negative 1. Now when we say positive and negative, it's similar to slope. And actually, R determines the slope of this line. But anyway, so negative would mean that the line goes down. Positive means the line goes up. The closer this number is for R to positive 1, the stronger the relationship. Right now I have 0.696. Is 0.696 really close to 1? No. Is it really close to 0? No. It's kind of in between. 0.696 would fall into the category of it's a moderately positive linear relationship. Moderately strong. I mean, you could even say it's mostly linearly related. Again, correlation is it assesses how linear the relationship is. All right, so this is a mostly linear, moderately to weakly positive linear relationship. Which means, that's that phrase that I say many, many times. So interpreting the correlation coefficient, since R is 0.696, there is a weak to moderately strong linear relationship in the positive direction, which means as exam 1 scores go up, I would expect, that's the hat, I would expect the exam 2s to also go up. So in the interpretation, there's that which means, and then you explain it in context of what the question was asking. So that's the correlation coefficient. The coefficient of determination is R squared. And in this case, it's 0.4845. The coefficient of determination explains to us how this equation predicts this value. All right, so I'll say it out loud once, then I'll even try to write this down in terms of an interpretation. R squared will typically then be rewritten as a percent. And here's how it would be stated. 48.45% of the variation in my expected exam values can be attributed through this equation to the variation happening in exam 1 values. So 48.45% of the variation that we see in expected exam scores can be attributed to the variation in exam 1 scores through this equation. Conversely, about 51.5%, right? The opposite of this, the complement of this, about 51.5% of the variation in exam 2 is attributed to something else. There's something else not associated with exam 1 that it goes towards the exam 2 variability. That's a 1. All right. So 48.45% of the variation in predicted exam scores is attributed to the variation in exam 1 scores using this equation. Then 51.5% of the variation in exam score for 2 is attributed to something else, not related to exam 1 using this equation. So then, as we move on, these are the other questions off that first slide, or actually the second slide. Based on the regression equation, what should the person who scored 71 on the first exam get on? So this is what they actually got. They actually got a 65. What should they have received? Take a moment. Figure that out for yourself. It's pretty simple, quick calculator activity. What is the value that they should have gotten? 71.4. Hold on. And for x, we take this number, put it in for x. What'd you get? 71.4204. 4204. All right, so they should have got 71.4204. Is that better or worse than their actual score? Their predicted score is higher than what their actual score is. When your predicted score is higher than your actual score, you are said to have a negative residual. And I think my next... when you did your plot on Stat Blue, did it give you a residual plot right underneath your regular plot? Yes, I'm seeing some nods. That's good. What I want you to do with your mouse is hover over the data point on the residual plot. So you're on the residual plot. Go to that. Hover over the data point that has an x value of 71. There's only one of them. And when you hover over that plot, and I'm just going to have like, right, our plot looked something like this. We had a line, we had data points. 71, 65, I know is under the point, 65, because this right here above it was supposed to be 71.420. That's what it was supposed to be if I plugged it in the equation. But when you hover over it, I believe it tells you the residual of that data point, does it not? Yes, it does. What is the residual of that data point? Negative 6.42. Because 65 is 6.42 below the predicted value. Now you're going to see in books and things like that where it's going to give you an equation for the residual. You can memorize that, write it down all you want, but ultimately you have to just remember this. If my actual point is below the line, it's a negative residual because I am below the line. If the actual data point were above the line somewhere, its residual will be positive because it is above the line. The harder part becomes if someone says, hey, it had a negative 6 residual, what does that mean? That meant that the prediction line overestimated the actual value. A negative residual means the prediction line overestimated the actual value. So here's where, even in a scenario where maybe you're given a multiple choice question or something like that, or you don't even know the numbers, make a little sketch to, all right, so it's the actual point is below the line. That's what negative means. That means the prediction line predicted a value that was higher than the actual value. This overestimated that. Line? Nope. So then, what we're going to do, so now we've got this idea that this is what a line regression is. At the very end of class, I'm going to have a couple slides and I'll show you the big formulas and the theory behind where all these numbers come from, which you'll never have to do by hand because they're very laborious. But you'll see where they come up and how they're related to each other. If you decide to further investigate statistics as a career option later in your life, you're going to come back to this and go, oh, I saw that once. Don't remember any of it because it was a long time ago, but maybe you will. All right, so now we're going to actually go to this idea. Is the relationship linear? So is the relationship linear? We're going to be conducting a hypothesis test on the correlation coefficient. My hypotheses for the correlation coefficient. So again, the correlation coefficient, the letter that we use for that is R. So for Greek letters, we choose the letter rho. It's not a P. It's like this. That's a better looking one. It's rho. So if there is no linear relationship, what number did we say that R was if there's no linear relationship? 0. It's -1 if there's a strong negative relationship. So if it's going top to down, but it's very, very, very linear top to down, that's a -1. If it's very, very, very linear going up, I'm +1. But if there's no relationship at all, my R is 0. So my rho would be 0. In this case, I'm testing, is there a linear relationship? So I want to test to see, is rho not 0? My conditions for this kind of work, there's actually a lot more conditions. The first condition is I have to assume that each of my x values and my y values individually are normally distributed. And I would expect that my predicted values for any given x would be normally distributed. We're not going to spend much time on the conditions. We're just going to go with the idea that if the original populations of the two values, the exams on this question, exam 1 and exam 2, if they are each individually normally distributed, I'm going to go ahead and use a student's t-distribution. There's another condition in there. Are they independent of one another? Now, in this case, you might say, well, one, like this should not be independent of that one. But I'm saying, is this person independent of this person when they took their exams? Again, if we assume academic integrity and they weren't cheating, then yes, one person's scores on either of the two exams does not influence someone else's scores on either or two of the exams. All right? This 70 and that 76 are probably not independent. All right? Because it's the same person. You would assume that there's something about if you knew what you did on your first exam, that's going to have an influence on how you do on your second exam. Could spurn you on for greater things. Could make you feel intimidated and come in and freak out and score worse the second time. There's a lot of things that go on in an individual person that's going to make one exam either go up or an exam possibly go down. All right, but independence is between every individual person taking tests, and then the two different exams themselves are going to be normally distributed. So there's my hypotheses again, and here's my formula. My degrees of freedom is n minus 2. The reason why it's n minus 2 is I have an x and a y. So instead of just one list for a t-distribution, I have two lists of data. So instead of n minus 1, it's n minus 2. All right. This will be important because the regression analysis that the online StatBlue program does is not for this. It did it, if you did it in your example, it does it for beta, which is slope. We're doing it for R, which is coefficient, correlation coefficient. All right. We'll cover this here just probably in a couple slides later on how to do that. All right. So for this, we're actually going to need to pull that up in StatBlue and remember what those numbers are. But this is the formula right here. R times the square root of n minus 2 all over the square root of 1 minus r squared. All right, if you want to, we can put words to this. It's actually the correlation coefficient times the square root of the degrees of freedom divided by the square root of 1 minus the coefficient of determination. That's what all those things are that are inside of there. But if we do, over here on the left, plug these numbers in, so that's, my square root symbol disappeared. There's a square root sign right there. There we go. 0.696 times the square root of 10 minus 2. There were 10 pairs of data. Right? There were 10 points on that graph. That's why it's 10. Some mistakes I see is individuals will say, well, there's 20 points, which is true, but there's 10 pairs. So it's 10 data sets, 10 points on that graph, 10 minus 2. And then 1 minus 0.696 squared. And I'm also missing the square root there. There it is. On the applets page, now's the time you're going to go to the applets page. You're going to put in 8 degrees of freedom. It'll make this t-distribution. And then you're going to put in this value, 0.27416, right here. And this needs to match up with my alternative hypothesis. My alternative hypothesis that we did was HA, rho does not equal 0. Does not equal to means two-tailed. If it's greater than, it's the upper tail. If it's less than, it's the lower tail. When it's not equal to, it's both tails. You'll get a t-score here. And if you're not already there, go to your StatBlue and put it in to find, and then change that drop-down menu so it's the not equal to. And if you do one and then you hit calculate and you look at your picture and realize, oops, that's the wrong thing, then choose the other one, then hit calculate again. So you get it as the two tails. What is, so this is my p-value in that little spot. Did anybody do it and can tell me what number they got for their p-value? 0.02538. Okay. And again, if you rounded and got something slightly different for a t-score, you put it in there, you might get a little something off by a fraction amount there as well. And this goes into the fact that when you're doing all of these problems, as we've talked through, conditions, hypotheses, formula, calculations, you show your picture, you show your calculations of what you got, so I can look and say, oh, okay, they're off by a little bit here or there, and that's why your p-value is different than whatever I had. Showing your work, showing the process. Process outweighs product every time. Now, if your process is 100% wrong, well, then your product will be as well. But in this case, even with rounding, you're going to get something like that. So my p-value, which is the two tails added up, 0.02538. All right. And ideally, you're using this time, you're checking the applets page, making sure you can find these same numbers. So come test day, you're not going, hey, where are those applets pages? I've never looked at them. You should have them bookmarked before coming into the exam. All right. So we did our calculations. We have our picture. What's our decision? What is our decision? Is that p-value too big or too small? Too small. Based on our arbitrary 0.05. This number is less than 0.05. It's too small. It's too small for what? It is too small to assume that the null is true. If the null were true, if my correlation coefficient were indeed 0, this number, our statistic that we have, would only happen 2.5% of the time. That's too small. It's so small that it makes me say, reject the null. Accept the alternative. My interpretation would be, there is sufficient evidence to show that the correlation coefficient is not 0, which means there is a linear relationship between exam 1 and exam 2 with the line of regression. Kind of redundant there with saying linear and line of regression, but so there is sufficient evidence to show that the correlation coefficient is not 0, which means there is a linear relationship between exam 1 and exam 2. And I'm hoping at this point, some of you are saying, all of these are starting to sound familiar in how we go about doing them, and that's because they should. A lot of the conditions will be in there about normality and independence, and do I know sigma? And then in terms of hypotheses, either the mu is equal to something, the p is equal to something, and now the rho is equal to something. And in a minute, it'll be beta is equal to 0. If beta is equal to 0, if the slope is 0, that means it's neither going up nor going down. We have a test statistic. We have degrees of freedom. We look at the stat applet for the t distribution. We put in our degrees of freedom and our boundary point. Our boundary point here was the 2.7416. This is related to my alternative. I get results. Interpret my, or reject or accept. Sorry, either reject the null or don't reject the null. And then interpret what it means in context for the scenario. So in a linear regression model, this is what's going on. There's a lot happening. If you were like, how do you calculate R? Right here. So if I take each data point, take the X value and the Y value for that data point and multiply them, add them all up, and then multiply by, in our case, 10, because there are 10 data points. Then I'm going to subtract. I add up all the X's, I add up all the Y's, I multiply those, I add those up. Down here, I take each X and square it, add them all up. I take the sum of all X's and square it. I subtract them from each other, but not before multiplying the first one times 10. Like I said, there's just a lot going on here to find R. This is a very complicated process to determine the coefficient, the correlation coefficient. In my equation, y hat equals a plus bx, it goes through the point. So the line that we're plotting, so on the one that we plotted, if you looked at that data, one data point was really close to being on that line, but actually none of them are. The one point that the line of regression goes through is the point x bar comma y bar. So if you found the average of the x's, found the average of the y's, plotted that point, that's where the line of regression will go through it. I will then use R to find the slope. The slope is R times the standard deviation of y or the standard deviation of x. And again, you're not going to ever have to do this by hand, but if you look at this and you think back to slope, slope was delta y over delta x, change in y over change in x, rise over 1, rise over run, y2 minus y1 over x2 minus x1. However you want to think about, that's what slope is. Here we're talking about change in y, the average distance of every data point from the y mean. The average distance of every data point from the x mean, delta x. And then we multiply that by the strength of linearity. So if R is 1, then it's exactly sy over sx, where we'd say, yeah, all the variability in y is coming straight from the variability in x. If R is 0.9, then 0.9 of the variability in y over the variability in x is associated with what's going on in my equation. Ours was 0.696. And then there's the equation. Oh, I rewrote it up here again. Y hat equals a plus bx. All right, there's two different ways. I can find the slope this way, or I can find the slope this way. This is a shorter, typically, way to find it. If you had to do it by hand, which outside of technology completely failing and you needing to figure this out in the apocalypse, also unlikely, this is how you would have to do it. But then you have to go back and remember what the formulas are for standard deviation of y and standard deviation of x. Which leads us into, then, our grades improving. That is, if they're not improving, the slope is 0. If they are improving, the slope is greater than, not greater than 1, greater than 0. It's a positive slope. If grades are improving, there would be a positive slope. Because you put in an x, the y value will be higher than that, so it's a positive slope. My conditions will be the same as they were before. Are my x variables approximately linear or approximately normal? Yes, I said, because in the stem of the question it said, assume that the values of the exams for each of the exams are normally distributed. So exam 1 is normal, exam 2 is normal. Every individual data point, every individual person will be independent of every other person in there, so there's independence. My formula, t equals, it'll be b minus beta over the standard error of b. In the past, we had, for doing means, that's an S, t equals x bar minus mu over s over root n. S over root n is the standard error of x bar. So then, we go back to this. Off the StatBlue website, if you selected the little box that said include regression inference, beta is 0, we need to change it to be beta greater than 0. So if I make beta greater than 0, because that was my alternative hypothesis, alternative was, can I show that the grades are improving, going up, positive slope? You can choose whatever alpha, but it usually defaults to our arbitrary. No one really remembers why it matters, but we do. We say it's 0.05. Y equals alpha plus beta x. That's the true one. Degrees of freedom was 8. The slope estimate was this. Standard error of the slope was that. So if I would do t equals b minus beta over standard error of beta, we get 0.9814 minus 0. That was my b. 0, because we started and said that beta will be 0. We're going to assume there's no relationship. Divided by 0.3579. 0.9814 divided by 0.3579. Yes, good. It should equal the test statistic that they give you. Right here. Oh, I see what's happening. All right, well, my pen is starting to fail, so I'll just go with the finger here. Right there, 2.7419. Again, depending on rounding, my p-value, 0.0127, which is very low. I will reject. Oh, I forgot to draw my picture. T, right there, 2.717419. Shade up here. It's the right tail shaded because I'm testing for greater than. Greater than, right tail. And I used to teach this. As long as you write your variable first, beta, you can also look at that and say, which way is that arrow pointing? The arrow is pointing to the right, so I'm shading the right tail. I know some people have struggled in the past with greater than, less than. How do you read it? You never really figured it out. If that's pointing to the right, I shade the right end. If we're pointing the other way, I would shade the other end. If it's not equal to, it's both ends. Anyways, this is really low. Reject the null. Like, very confidently reject the null. Accept the alternative. There is strong evidence, because that's really small. There is strong evidence to show that the exam 2 grade will be greater than the exam 1 grade. The slope is positive. It's a growing function. And then lastly, when you did this in StatBlue, it gave you these. If you've not seen these are fun. They are good to use. You'll be needing to know what goes on if you're given these images on the exam and say, what does this tell you? That's kind of what you're going to be asked. All right? You're not going to be asked to draw the graph. The graphs will all be given on exams, but interpreting what they mean. This graph was the original graph of my data. The red line was the line of regression that we calculated. The blue line is a 95% confidence interval line, which means if I have a value of, like, say, 75 right here, if I go up, the predicted value will be right here, which looks like it's also about 75. But I'd be 95% confident that the actual value from the predicted is somewhere between here and here. 95% prediction interval is then between these two here. So that's what the green and the blue mean. The green and the blue mean here. For a number to be considered an outlier, because this one almost looks like it is, to be an outlier, it would have to be outside of the green lines. Which is why, like in a t-distribution, when we did this for means, when we had a small sample size, something less than 40, we said, hey, can we use the t as long as there's no outliers? After 40, sample size over 40, then we can use a t for just about anything. And we're not going to worry about outliers even if they do exist. But between 15 and 40, for just a regular single t-distribution, we had to show there's no outliers. The same thing goes here. You would do this and say, hey, are all the data points within my 95% confidence interval? Plus or minus 2 standard deviations. Right? Empirical rule, it's going back to that. Plus or minus 2 standard deviations. Empirical rule, 95% of the data is within 2 standard deviations of the mean. 68, 95, 99.7 were those numbers that we had. So as long as I'm within 2 standard deviations, which all these data points are, for residuals and for here. So if these values got turned and just looked at residuals, then they become horizontal lines. As long as they are, then I have no outliers, and I can continue on with this small data set, which is 10, and do my regression analysis. So theoretically, if I were doing this the right way, I would have done the residual plot and this plot right away as part of my assessment of normality, independence, and making sure there's no outliers. No outliers, I can continue on. So this would have actually been part of my conditions. Plot back here, the lowest value I had was 60, or in this place here, right? 60 for x, so 50 would have been lower yet. But 50 would have been within that, so that would be a better argument, although still incomplete. We all had an AP Stats in the past and talked about this. My data, my lowest data point down there has a value of, was it 60 or 61? My actual data points for x's, 61, okay? My lowest data point is 61. The endpoints. Between 61 and whatever that one was, 88 or something, or 89, if I'm within those values, I can use this equation to make a prediction. Because I have absolutely no idea what happens after it leaves here. Maybe they taper off or go down, or maybe they suddenly go up. I have no idea what goes on after I leave this end because I have no data from that end. And then the last idea here before we cut out for the day. What if someone scored a 50 on the first exam? What would I expect they get on the second exam? And can I trust this estimate? Take a moment, first figure out the number, and then turn and talk to the person next to you about what we've talked about so far today that you could use as evidence to support your answer of can I trust this estimate? Oh, that's getting a bill on me. What is my exam 2 predicted grade going to be? 54 point, oh, sorry. 50.811. All right. I see some other bobbleheads confirming that is the number. So then the follow-up question is, can you trust this estimate? Jared's shaking his head no. Why, Jared?
Because we rejected the null.
What was the null again? The null was that the slope is 0. So I said, yes, there's a positive slope. That's what the alternative hypothesis was. I said there's strong evidence that there's a positive slope, which means as x goes up, y goes up. So did this go up? Yeah. So to use your argument, that would be, you would say, yes, I can trust it because this number does go up from that one, and we just proved that it did. Well, we'll come back to that. Does anybody else have a different reason to support whether or not they trust this estimate? Okay, you're saying because they fell between the green lines? Okay, which would be an interesting argument, a better argument saying because 50.811 would fall between the green interval lines if you would extend it down. All right, because in my actual... All right, this is where I didn't know if maybe some of... This one is 50. It is outside, it's outside of the data that we had selected. When we make predictions, we can only make predictions within, it's called extrapolation. You cannot use a regression model to extrapolate. If I look within the interval, it's called interpolation. I can interpolate data, but if I extrapolate, I really risk a lot of things because I have no data to show that this trend will continue outside of that data point. Probably the biggest thing that made the news well before you were born that happened as a result of extrapolation was Space Shuttle Challenger was scheduled to blast off on I want to say a late February morning in South Florida, and the temperatures were low. The temperatures were actually below any temperature they'd ever tested the solid rocket booster at. And what they found out afterwards, because the Space Shuttle Challenger blew up as it was trying to accelerate, got to the second, not to even the second stage, but the solid rocket booster, there was a small puff of smoke that they saw at one of the joints of the metal of the cylinder, and immediately after that little puff that they saw, the whole thing just blew up because what's called an O-ring, if you think about like a hose, you got like a little rubber gasket. When you tighten your hose on the hose thing at home and you turn the water on, no water should come out. When that little ring goes bad, water comes out. In this case, it was liquid oxygen possibly that came out. So at the minute there was a spark, then it blew up because that O-ring failed. But they had extrapolated from previous data and said, well, we assume this trend will continue even into lower temperatures, so we should be fine. All right?
But they were wrong.
They were wrong, but this is also why don't extrapolate. Now, not in this test case scenario, but extrapolation can kill you. You only know what happens within the values that we have. Outside of it, anything can change. And we cannot make predictions outside. All right? Unfortunately, news people don't know this. They do extrapolating all the time. They see data that comes out of somewhere and say, oh, that means we're headed here. I'm like, we don't know that. We have no data to support that. We can only talk about what happens within the range of values that we have. Interpolation is okay. Extrapolation, not so much. All right. That's all I got for today.